One of the main motivations for why we study graphs is the ability to identify routes. This can come up in sending data through a computer network, planning a road trip itinerary on a map, measuring the spread of a social network, and many other applications. So let's establish some formal definitions that will let us talk about routes through a graph. First, we can define a walk as some sequence of vertices where each vertex in the walk is adjacent to the next. So an example of a walk in this graph could be going from A to H to B to C to H to F to G to I to G. And so we could write the list of vertices that make up this walk. And of note, our definition of a walk allows us to visit the same vertex multiple times and traverse the same edge multiple times. But if we want to disallow those things, we can talk about paths. A path is a walk, so it is also a sequence of adjacent vertices, but it has no repeated vertices. So for example, CDELM is a path because no vertex appears more than once. And of course, if we can't visit the same vertex more than once, that also rules out the possibility of traversing the same edge more than once. For any walk, including paths, we can define the length of the walk to be the number of edges, and importantly, the number of edges is one less than the number of vertices, so we define that to be the length of this list minus 1. The notion of length, when applied to paths, allows us to define the distance between two vertices as the length of the shortest path. So for example, between I and L, there are many different paths. We could go by way of N and M, or we could go by way of H, but the shortest path is length 3, IJKL, and so the distance from I to L is 3. On the other hand, for some pairs of vertices, there might be no path between them. For example, from I to R, this graph has no path. In that case, we say that those vertices are not connected, whereas if there is a path, we say the vertices are connected. And if two vertices are not connected, then we say that the distance between those two is undefined. We'll also sometimes be interested in walks that have the same start and end point, and such a walk is called a cycle. This walk, NJKMLKJIN, has the same start and end point, and so we call it a cycle. Now that we have all this terminology, we can use it to start thinking about various properties of graphs. With our definition of connected, we can think about the is connected to relation, where AH or AE would be in that relation, but AP would not be. And we can prove that is connected to is an equivalence relation. To show that something is an equivalence relation, we need to prove that it's reflexive, symmetric, and transitive. And since this relation is on the vertices of the graph, we need to show that every vertex is related to itself. That every vertex is connected to itself may not be immediately obvious, especially because we defined connected in terms of a path, and a path cannot repeat a vertex. But our definition of a walk said that for each consecutive pair of vertices in the list, they must be adjacent. And so if we have a walk with only one element, the adjacency criterion is vacuously met, and so a list of just one vertex is a valid path, and so every vertex is connected to itself. To show symmetry, we need to prove that whenever U relates to V, V also relates to U. So for any pair U and V, where there is a path from U to V, just reversing that list gives us a path from V to U, so our relation is symmetric. Finally, to show transitivity, we need to argue that if U is connected to V and V is connected to W, then U is connected to W. And so, from the presence of paths U to V and V to W in the graph, we can think about concatenating those paths. If we concatenate two walks, the first one must have the same last element as the first element of the second path, and we then put the lists together, removing one of the copies of that repeated element. And this concatenation of two walks always gives us another walk. But to prove that U is connected to W, we need to show a path from U to W, and this walk might not be a path. In particular, suppose we have a path from C to M, and then we also have a path from M to A. And when we concatenate those paths, we get C, D, E, L, M, L, E, H, A. And that is not a path. But whenever we have a walk that repeats vertices, there is a sublist that is a cycle. Here, E, L, M, L, E is a cycle. And so we can take out all but the first vertex of that cycle, and we still have a valid walk. And so if we do this to all of the cycles in the walk, the result will be a path. And so if we follow that procedure and remove the cycles from this walk, we will have a path that starts at U and ends at W. Note that I didn't list V as a part of this path because, as we saw in our example, V might end up being part of one of the cycles that is eliminated. But no matter how many cycles we eliminate, U will still be the first vertex and W the last, and the result will be a path from U to W, giving us transitivity. Now that we know that connectivity gives us an equivalence relation, we can think about the equivalence classes of that equivalence relation. On our example graph here, what things are connected to A? Well, it's all of the things that have some path from A, and that is all of the vertices except for P, Q, and R. So this graph has two equivalence classes, one containing A and most of the vertices, and one that contains P and the two vertices it is connected to. We call these equivalence classes components of the graph. So the set PQR is a component of this graph, and we can call a graph connected if that graph has only one equivalence class under the is connected to relation. So this graph is not connected, but if we added one edge, say from R to I, then the graph would be connected. And the idea of connected for two vertices and connected for a graph are closely related. A graph is connected if and only if every pair of vertices in the graph is connected. Finally, I'd like to consider a couple of properties that walks or paths might have. Namely, a walk is Eulerian if it traverses every edge exactly once, and a path is Hamiltonian if it visits every vertex exactly once. Under these definitions, it's clear that none of the walks we've drawn so far are either Eulerian or Hamiltonian. So let's reset our graph and think about whether it has any walks that meet these criteria. With our graph mostly restored, we can think about whether there is any walk that traverses every edge exactly once or visits every vertex exactly once. But immediately we see that with two separate components, there's no hope of finding any such walk. So let's add back the edge that makes our graph connected. And now we can try looking for an Eulerian walk or a Hamiltonian path. For an Eulerian walk, since we're trying to traverse each edge exactly once, we're going to need to either start or end at vertex A. Because if we try to visit it in the middle of our walk, clearly there's no way to get back out without reusing the same edge. From here we have several choices, but let's just arbitrarily try one of them. From here there are two edges from vertex K, where we need to eventually traverse both of them, but if we go to L now, then we're stuck, whereas if we proceed, there will be no way to get back to L later. And it's worth thinking about whether there's some way we could have avoided this problem. For example, if we had arrived at K and L from some other direction. But it seems like if we had come in from this direction, we would be facing the same problem. Either we go straight across to L and we miss these edges, or we go down to M and then we'd be stuck with the same sort of situation between these two edges. So it seems like for this graph there is no Eulerian walk. But what about a Hamiltonian path? In that case, we're not required to use every edge, we just have to visit every vertex. So again, we should either start or end at A. But now it seems like we've run into a sticking point where we have only two options and we can either go and visit G and F, or we can go visit P, Q, and R, but we don't have a way to visit both. But is there something we could have done differently to avoid getting stuck here? Well, in this case it turns out no. This graph does not have a Hamiltonian path, and the reason is that there's no path that can visit all of A, PQR, and GF. But even though we were able to determine that our example graph had neither an Eulerian walk nor a Hamiltonian path, it turns out that in general, the difficulty of these two problems is quite different. And so to start thinking about these properties in general, we can identify some things that must be true about a graph in order for it to have a Hamiltonian or Eulerian walk. And if we start thinking about what does it look like when a graph has an Eulerian walk, we can immediately deduce some things that must be true about that graph. If we imagine a walk that traverses every edge of the graph, Well, for starters, we know that we don't have separate components that each contain some edges. Otherwise, there would be no way to traverse them all. We don't necessarily have to have a connected graph, because there could be some vertex off by itself that has no edges, and we would still be able to traverse all of the edges on our walk. But if there were any other vertices in this component, that would mean they are connected by some edges. But if they are not connected to the rest of the graph, there's no way our walk could get there. Second, if we have some Eulerian walk, then we can think about all of the vertices that aren't the start or end of the walk, and those vertices have to have even degree. Recall that the degree is the number of edges, and so what went wrong here was that we had a vertex in the middle of our walk that had an odd degree. How do we know that this is true of every vertex other than the start and end of our walk? Well, each of those vertices must appear some number of times in the walk. That number of times could be 0, or 1, or more than 1. But each time a given vertex appears, we come into that vertex and back out by two different edges. And if it appears later, the same will happen. And because we know the Eulerian walk traverses every edge, there can't be any other edges coming out from this vertex except the ones that we followed as a part of the walk. And so the degree of this vertex will be twice the number of times it was visited by the walk. Unless, of course, it is the start or end vertex, in which case we could arrive here and never leave, or leave here without first arriving. And we can also deduce that the first and last vertices in the walk must have degrees of the same parity. If the degree of the first vertex is odd, then the degree of the last vertex will be odd. And if the degree of the first is even, then the degree of the last is even. How do we know this? Well, if all of the other vertices have even degree, then we can think about the sum of all degrees in the graph. In any graph we might draw, when we add up all of the degrees, that total must be even. Why is this? Well, it's because the sum of the degrees is twice the number of vertices. Because when we add up the degrees, each edge incident on I will contribute 1 to its degree, and each of those edges will also contribute 1 to the degree of some other vertex. So when we add up all of the degrees, each edge appears in that sum twice, so we get twice the number of edges. Then if the sum of all of the degrees is even, and everything except for these two vertices has even degree, then the remaining degree must be even. And so either we have that these two degrees are both even, or they're both odd, in order to ensure that the total degree is even. But it turns out that there's actually an if and only if relationship between these properties and the graph having an Eulerian walk. I've just sketched for you the forward implication, which shows that these are necessary conditions for a graph to have an Eulerian walk, but it turns out that they are also sufficient conditions. If you check these three conditions and they all come up true for a given graph, then you can conclude that that graph must have some Eulerian walk. I am not going to prove this direction of the implication, but it is covered in detail in your reading in the textbook. And if this topic is of interest to you, then that's a pretty good sign that you would be interested in taking our upper-level class on graph theory. Because these sorts of proofs about graphs and their properties are exactly the sort of thing that you do in much greater detail in that class. Finally, let's return for a moment to our other type of walk, a Hamiltonian path. For a graph to have a Hamiltonian path, we know that the graph must be connected because we have to visit every vertex. But for this question, it turns out there's not a lot more I can say. You can identify a few other necessary conditions for Hamiltonian paths, but we don't have a nice set of sufficient conditions the way we do with an Eulerian walk. It turns out that the question of whether a given graph has a Hamiltonian path is very difficult to solve. In particular, this is a problem that you might study in a theory of computation class, where you would prove that the problem of determining whether a graph has a Hamiltonian path is NP-complete. NP-complete means that there cannot exist an efficient algorithm to solve the problem unless the conjecture that P is not equal to NP turns out to be false. But that conjecture, which you can learn all about in theory of computation, is probably the most famous open problem in all of computer science.